Hi everyone. In this video I'm going to go over this practice questions for chapters 3 and 4, and down below in the description of the video you'll find a couple things. One, you can download a copy of this. You can also download a copy with the answers on it, and also you'll find a list of each of the questions, and there's a time next to them. So if you want to watch some specific questions, you can just click on those questions and the time link, and it'll just jump you right to that part of the video. So without going into anything else, let's get started with question 1. So question 1 asks, what is the classification for this reaction? Well, there's basically 5 types of reactions that we need to know. And the first is A plus B yields AB. This type of reaction is called a combination. We have the opposite of that. AB yields A plus B, and this is called a decomposition. We also have AB plus C yields AC plus B. So B is replaced by C in this type of reaction, and this is called a single replacement. We have AB plus CD, where A goes with D and C goes with B, yields A D plus CB, and this is called a double replacement. Then finally, we have CXHY, so some number of hydrocarbon with carbons and hydrogens, plus O2 as a gas yields CO2 and water, and this is a combustion reaction. So these are the 5 basic types of reactions that are covered here in this question. So if we look at these answers here, and basically what we want to look at is which type is this. Well, if we look, we have iron 3 oxide, which is rust, reacting with aluminum. So in this case, aluminum is replacing iron, and we end up with aluminum oxide and iron. I believe this is a thermite reaction. So when we have this here, this replacement occurring, aluminum replaces iron, and now iron is by itself. Well, that's a single replacement. C replaces B, and now B is by itself. So this is a single replacement type of reaction. All right, question 2 says, how many moles of N2O4 are in 76.3 grams of N2O4, and we have the molar mass? Well, if we want to convert from grams to moles, we want to use the molar mass, which is from the periodic table. So 2 times 14.01 for nitrogen, plus 4 times 16.00 for oxygen. The molar mass is on the periodic table, and that gives us our 92.02. So if we start with 76.3 grams of N2O4 times, well, we want to put the molar mass, 92.02 grams of N2O4 on the bottom, and on top, 1 mole, because this is grams per mole, 1 mole of N2O4. Multiply by the top, divide by the bottom, and when we round to the appropriate number of significant figures, we get 0.829 moles of N2O4. So converting grams to moles is something that's very common in chemistry, and you need a molar mass in order to do that. And for this question, the answer is choice letter C. Question 3 says, in this reaction, what is the correct coefficient for sodium chloride? So we have lead 2 nitrate reacting with sodium chloride to form lead 2 chloride and sodium nitrate. So in order to do this, we need to actually balance the entire equation. So when we do this, I'm just going to start from the left-hand side, and I see that there's 1 lead and 1 lead. When it comes to nitrate, I want to balance the entire nitrate. So I don't want to look at this as 2 nitrogens and 6 oxygens. Instead, I want to look at it as 2 nitrates. If I look over here at sodium nitrate, I notice there's only 1 nitrate. So I now want to put a 2 here. Now let's look at sodium. Here there's 1 sodium, and here now there's 2 sodiums, so I put a 2 here. Let's check chlorine. 2 NaCl's, so that means 2 chlorines, and we have Cl2, so we're good to go. It asks us for the sodium chloride coefficient, which happens to be 2. Note that in order to do this, I have to balance the entire equation to find the coefficient for sodium chloride. Question 4 is very similar to question 2. It says how many molecules of N2O4 are in 73.6 grams of N2O4, and it gives us the molar mass. If we look at back up to question 2, it's how many moles of N2O4 are in 73.6 grams. So it's the same mass, but in this case we want molecules. Well, in order to find molecules, we first have to find moles. So as our plan of attack goes, we want to convert from grams of N2O4 to moles of N2O4. And then finally to molecules of N2O4 using Avogadro's number. So here I want to start with 76.3 grams of N2O4 times. Well, if I want to convert from grams to moles, I need to use the molar mass. I want to put the mass on the bottom, 92.02 grams of N2O4 on the bottom, 1 mole of N2O4 on top. Now that I have moles, I want to convert it to molecules using Avogadro's number. And Avogadro's number is 6.022 times 10 to the 23. And that's the number of atoms or molecules in 1 mole. So at the bottom, I want to put 1 mole of N2O4. And at the top, I want to put Avogadro's number, 6.022 times 10 to the 23 molecules of N2O4 in this case. When I do that math, multiply by the top, divide by the bottom, multiply by the top, divide by the bottom, I find that there are 4.99 times 10 to the 23rd molecules of N2O4 in this example, and that is choice letter D here. Question 5 asks us to calculate the mass percent of sulfur and aluminum sulfate. So mass percent is the mass of the element divided by the mass of the compound, or the molar mass, times 100, because it's a percentage. So we're going to assume that we have 1 mole of aluminum sulfate. And therefore, the mass percent is equal to the mass of sulfur divided by the mass, or the molar mass, of aluminum sulfate times 100. So to figure this out, we need to find the mass of sulfur. Well, to figure that out, we need to figure out how many sulfurs are in this compound. So if we look, aluminum sulfate has 3 sulfates. Each sulfate contains 1 sulfur, so we take 3 times 1, and we know that there are 3 sulfurs. So we look up the molar mass of sulfur, so we take 3 times 32.07 grams. We repeat the process now for the whole compound, so aluminum, there's 2 of them. The molar mass of aluminum on the periodic table is 26.98 grams, plus 3 sulfur still, 3 times sulfur, so 3 times 32.07 grams, plus 3 times 4, because there's 3 sulfates, each has 4 oxygens, there are 12 oxygens, so 12 times 16.00 grams. And we take all that and we multiply by 100 because it's a percentage, and when we do that math, we find that it is 28.12% by mass sulfur. The next question says, what is the empirical formula of C6H12O6? Well, an empirical formula is the simplest ratio of moles. So if we have C6H12O2, I think I said O6 before, but it's C6H12O2, we need to look for a common denominator. And in this case, that common denominator is 2. So if we take this, we divide by 2, take this, divide by 2, and take this, divide by 2. What we find is C, 6 divided by 2 is 3. H, 12 divided by 2 is 6. O, 2 divided by 2 is 1, so we don't write it. So the empirical formula of C6H12O2, or the simplest ratio of moles, is C3H6O, choice letter D. Question 7 asks, determine the empirical formula for a compound that contains carbon, hydrogen, and oxygen. And it says it contains 52.14% carbon and 34.73% oxygen. And the rest of 100% must be hydrogen, even though it's not given here. The first thing we want to do is we want to assume that we have 100 grams of this compound. Why? Because if we have 100 grams of this compound, we'll have 52.14 grams of carbon. A unit we can use. Percentage is a hard unit to use. And if we have 100 grams of this compound, we'll have 34.73 grams of oxygen. And if we take 100 minus 52.14 minus 34.73, so subtract both of these from 100, we find out that we have 13.13 grams of hydrogen. Now, if you recall from the previous problem, if you watched that one, we talked about how an empirical formula is the simplest ratio of moles. Well, here we have grams, we don't have moles, so we need to convert these grams into moles. To do that, we use the molar mass, which for carbon is 12.01 grams of carbon per 1 mole of carbon. And when you do that math, you find out that there are 4.34 moles of carbon in this sample. Next, we need to do this for oxygen. So we need to convert from grams of oxygen to moles of oxygen. So we use 16.00 grams of oxygen, and on top 1 mole of oxygen. And when you do that math, you find that there is 2.17 moles of oxygen. Repeat for hydrogen using the molar mass of hydrogen, which is 1.01 grams of hydrogen per 1 mole of hydrogen. And when you do that math, you get 13.0 moles of hydrogen. Well, now we have the moles of carbon, oxygen, and hydrogen in the compound, but we still don't have the empirical formula. Remember that the empirical formula is the simplest ratio of moles. So what we want to do is we want to find a whole number ratio of these. Said another way, we want to divide by the smallest. So our choices are 4.34, 2.17, or 13. And 2.17 is the smallest. So if we divide 2.17 by 2.17, we get 1. We also want to take 4.34 divided by 2.17, and we get 2. And we want to take 13 and divide by 2.17, and we get 5.99 or something, which is approximately 6. So now we can see we have 2 carbons, 1 oxygen, and 6 hydrogens. We write carbon first, C2, H6O. And this is the empirical formula of the compound, which is choice letter E. Question 8 says, consider the following balanced reaction. How many grams of water are required to form 75.9 grams of nitric acid, HNO3? And it says, assume there's excess NO2 present. So basically we have a balanced chemical reaction. We're given a mass of water to start with. We know we have plenty of NO2 to complete the reaction. Said another way, we know that water is a limiting reagent. And we want to figure out how much nitric acid we can make. This is a very typical question, and in fact the next 3 questions essentially do this same idea repeatedly. So what we want to do here is we want to convert from grams of water to moles of water. And the reason we want to do that is because we can measure grams on a balance, but we need moles to use the balanced chemical equation to relate to moles of nitric acid. So once we, I apologize, we're actually starting this on the other side. They gave us the grams of nitric acid. So we're actually going to start with grams of HNO3 and convert it to moles of HNO3. Then we're going to convert to moles of water to figure out how much water we're starting with, and then finally to grams of water. So I think I said that backwards. So basically they give us an amount of HNO3 and we want to figure out how much water we needed to do that, assuming we had excess of NO2. And again, water is a limiting reagent, but we're trying to figure out how much water because it gives us the mass of HNO3 to start with. So if we start with 75.9 grams of HNO3 times, we want to convert it to moles. Well, we have the molar mass. So we put the molar mass on the bottom, 63.02 grams of HNO3, and that is the mass on the top of 1 mole of HNO3. Now that we have moles of HNO3, we want to convert it to moles of water, because the question also ultimately asks us how many grams of water are required. Well, to do that, we use the balanced chemical equation. So to convert from moles of one thing to moles of another, we need a balanced chemical equation. Well, in this case, we're trying to get rid of HNO3, so we put 2 moles of HNO3 on the bottom, again 2 moles because it's in the balanced chemical equation, and 1 mole of H2O on the top. Then we want to convert to grams of water. So moles to grams, we again use the molar mass like we did in previous problems, but this case we put 1 mole of H2O on the bottom and 18.02 grams of H2O on the top. To solve this, multiply by the top, divide by the bottom, multiply by the top, divide by the bottom, repeat until you get to the end, and in this case we get 10.9 grams of H2O, which is choice letter B. Question 9 asks us to determine the theoretical yield of HCl if 60 grams of BCl3 and 37.5 grams of water are reacted according to the following balanced reaction. And then it gives us the molar mass of BCl3. So essentially, to solve this problem, what we want to do is we want to figure out how much HCl we can make with all of our BCl3 and how much HCl we can make with all of our water. Whichever one is a lower amount will be, that reactant will be gone, and that's how much HCl we'll make. Said another way, whichever one makes less HCl will be the limiting reagent, and the theoretical yield will be the amount of HCl produced for when all of the limiting reagent is reacted. So in order to do this, it's very similar to the previous question, except we have to do it twice. So in this case, we want to convert from grams of BCl3 to moles of BCl3. And remember, we're trying to figure out how much HCl we could make, so we want to convert that to moles of HCl, and then finally to grams of HCl. We want to repeat this entire process for water to see which one we're going to run out of first. So we want to go from grams of water to moles of water to moles of HCl, and then finally to grams of HCl. So grams to moles to grams, just like in the previous problem, and actually just like in the next problem as well. So in this case, what we want to do is we want to start with 60.0 grams of BCl3 times, we want to convert those grams to moles. So on top, we put 1 mole of BCl3, and on the bottom, we put the molar mass, which in this case is 117.16 grams of BCl3. That happens to be given in the problem, but if it wasn't, you could use your periodic table of boron plus 3 chlorines and their molar masses, and you'd get it's 117.16. Now we want to convert from moles of BCl3 to moles of HCl. Whenever you're converting from moles of one compound to moles of another, you want to use a balanced chemical equation. Well, in this case, we're trying to get rid of BCl3, so we want that on the bottom. So we want to put 1 mole of BCl3 on the bottom. And then on top, we're looking for HCl, so we want to put 3 moles of HCl on the top. Finally, we want to convert to grams of HCl, so we need the molar mass. Well, we put 1 mole of HCl on the bottom, and then it's 1.01 plus 35.45, and what you end up with is 36.46 grams of HCl using the masses on the periodic table. Multiply by the top, divide by the bottom, repeat to the end, and in this case, you find that it's 56.0 grams of HCl. So what this means is if I use all 60 grams of BCl3, I will form 56 grams of HCl. Now I want to repeat this process for water and see how much I'll form. If it's less, then I'll form that amount. If 56 grams is less, then I'll form 56 grams. So we're going to do the same process, starting with grams of water. In this case, we have 37.5 grams of H2O. We want to convert that to moles. So we put on the bottom 18.02 grams of H2O, 2 hydrogens plus an oxygen on the periodic table, and on top 1 mole of H2O. In the next step, we want to convert from moles of water to moles of HCl. Again, moles of one thing to moles of another, you're always using a balanced chemical equation. So we want H2O on the bottom because we want to get rid of it. So we want to put 3 moles of H2O on the bottom, and on top, 3 moles of HCl. Finally, we want to convert to grams of HCl. So we have the same step at the last step of the dimensional analysis. Let me explain that better. So in the last step, we're going from moles of HCl to grams of HCl. In the last step down here, we're going from moles of HCl to grams of HCl. Since the last step is the same, the conversion factor is the same. So we can just copy this down. 1 mole of HCl on the bottom and 36.46 grams of HCl on top. And when you do that math, you get 75.9 grams of HCl. So what this says is if you react all of your BCl3, you'll make 56 grams of HCl. If you react all of your water, you'll make 75.9 grams of HCl. So you can only make 56 grams of HCl. Why? Because you have no more BCl3. You reacted all of it. If you have no more BCl3, you can't cause this reaction to go anymore. It stops. So in this case, this is called the theoretical yield. And although they don't ask for it, BCl3 is referred to as the limiting reagent. So it's the one that limits the reaction because we run out of it first. But the choice here is choice letter C. Note that 75.9 grams is also an answer here. So make sure if you're faced with a problem like this, you figure it out for both and pick the lower one. Question 10 is very similar to question 9, so I'm going to go through it relatively quickly, not very quickly. It says determine the limiting reagent and mass in grams of nitrogen that can be formed from 50 grams of N2O4 and 45 grams of N2H4. So essentially, we're given a mass of N2O4 and we're given a mass of N2H4, and we want to figure out how much N2 we can make. So what we're going to do is we're going to figure out how much N2 we can make using all of this reactant and how much we can use of how much N2 we can make using all of this reactant, and whichever one is lower is how much we're going to make, because we're going to run out of that reagent. So for N2O2, we want to convert from grams of N2O2 to moles of N2O2 to moles of N2, and then finally to grams of N2. We want to repeat this entire process for N2H4. So we want to go from grams of N2H4 to moles of N2H4 to moles of N2, and then finally to grams of N2. So we're going to do this whole job twice, just like in the previous problem. So starting with 50 grams of N2O4, I think this is N2O4. I think I kept writing as N2O2, but N2O4 times, we want to convert it to grams, or excuse me, to moles. So we want to take the 50 grams and convert it to moles. So what we want to do is we want to take the molar mass, 92.02 grams of N2O4, and on top 1 mole of N2O4. So that's how we do that first conversion. Then we want to convert it to moles of nitrogen. Remember, anytime you want to convert from moles of one compound to moles of another, you have to use a balanced chemical equation. In this case, we want 1 mole of N2O4 on the bottom, and on top, 3 moles of N2, because there's 3 in front of N2. Then we want to convert it to grams of N2 using the molar mass. So we put 1 mole of N2 on the bottom, and then we do 2 times 14.01, which is 28.02 grams of N2 on the top. And when you do all that math, you find that you'll make 45.7 grams of nitrogen by using all of the N2O4. Now we want to repeat this process for N2H4. But for N2H4, we start with 45 grams, because that's what the question says. So we start with 45 grams of N2H4 times. We want to convert it to moles. We're going to use the molar mass. So we put 32.05 grams of N2H4 on the bottom and 1 mole of N2H4 on the top. Now we want to convert from moles of N2H4 to moles of nitrogen. So we use the balanced chemical equation. In this case, it's 2 moles of N2H4 on the bottom and still 3 moles of N2 on the top. Now in the last step, we're doing the same conversion. Moles of nitrogen to grams of nitrogen, moles of nitrogen to grams of nitrogen, so we can use the same conversion factor. So we just copy this down. 1 mole of N2 and 28.02 grams of N2. And when we do all that math, we find out that it's 59.0 grams of nitrogen. So what this says is when we react all of our N2O4, we make 45.7 grams. When we react all of our N2H4, we make 59 grams. Well, after we make 45.7 grams, we have no more N2O4. If we have no more N2O4, we can't do the reaction anymore. So this is the theoretical yield. And the limiting reagent is the reactant that leads to the theoretical yield, or that gives you less product, if you will. So in this case, N2O4. So if we look at the choices, the limiting reagent is N2O4, and we make 45.7 grams. So this is the correct answer to this problem. Choice letter C. Question 11 says, when magnesium chloride is dissolved in water, which best describes what is in solution? Well, if we take magnesium chloride solid and we add it to water, we get Mg2 plus, because magnesium is 2 plus, it's a 2A, aqueous, and Cl minus, aqueous. But because there's two chlorines here, we have to get two Cl minus ions. So when ionic compounds that are soluble in water dissolve, or when ionic compounds dissolve in water, they break up into their ions. In this case, magnesium chloride breaks up into magnesium 2 plus and 2Cl minus, which is choice letter A. MgCl doesn't make any sense. It does not stay as MgCl2, and Mg is 2 plus, it's not plus 1, so therefore this answer is no good. Question 12 is similar to question 11, except that it involves HCl. So the first thing we need to remember is that HCl is a strong acid. It's hydrochloric acid. So it's going to be an acid, not a base. How does it behave in water? Well, what makes a strong acid is that if we have HCl gas, it will break up or dissociate in water into H plus aqueous plus Cl minus aqueous. So this dissociates like an ionic compound, but it's not an ionic compound because it has two nonmetals, right? Hydrogen's a nonmetal and chlorine is a nonmetal. So it's a covalent compound that happens to dissociate in water like this. This is called a strong acid. So that's kind of the definition of a strong acid. So when we look at the answers here, first of all, it's an acid, it's not a base, so it has to be B or D, and it forms H plus and Cl minus. It does not form H minus and Cl plus. That doesn't make any sense, so the choice here is choice letter D. Question 13 says, what is the concentration of chloride ion in 0.25 molar calcium chloride? Well, this is similar to the previous two questions in that we have to realize that if we have calcium chloride in solution, it'll break up into Ca2 plus aqueous plus 2 Cl minus aqueous. So if we have 0.25 molar, which is 0.25 moles per liter, we have 0.250 moles of CaCl2, that should be moles, CaCl2 per liter. Now, if we look here, for every one CaCl2, we have 2 Cl minus. So we can put 1 mole of CaCl2 on the bottom and 2 moles of Cl minus on the top. And when we multiply by the top, divide by the bottom, we find out that this is 0.500 moles of Cl minus per liter. Well, a mole of Cl minus per liter is a molarity. So in this case, the molarity of the chloride ion is 0.5. We had to double it because there's twice as many chlorides as there are calcium chlorides. Question 14 says, determine the molarity of a solution formed by dissolving 97.7 grams of lithium bromide in enough water to yield 750 milliliters of solution. And that gives us the molar mass. So molarity, which is abbreviated big M, is equal to moles of solute divided by liters of solution. And I like to do this by dimensional analysis. But the first thing that I realize is that this moles per liter, not moles per milliliter. So this is, I want to consider as 750 milliliters. I want to divide that by 1,000 and get 0.7500 liters. So the volume of the solution is in liters, not in milliliters. Now if I set this up to like dimensional analysis, I can convert from grams of LiBr to moles of LiBr. Why? Because I want moles of solute, not grams of solute, and LiBr is the solute. Then I want to divide it by liters of solution. So I want to divide by liters of, in this case, LiBr solution, and moles divided by liters gives me molarity. But how do I set this up in dimensional analysis? Let me show you. So if you start off with 97.7 grams of LiBr times, you want to convert to moles, so you put the molar mass, which is given 86.85 grams of LiBr on the bottom. On top, 1 mole of LiBr. Then we want to divide by the volume in liters. Well, if you want to divide in dimensional analysis, you put a unitless 1 on the top, and then you put the number you want to divide by, in this case 0.7500 liters, on the bottom. And what you'll end up with is grams cancel, and you'll get moles on the top, liters on the bottom. Said another way, you'll get molarity. Multiply by the top, divide by the bottom, multiply by the top, divide by the bottom, and you find out that this solution is 1.50 molar. Choice letter C. Question number 15 says, determine the oxidation state of carbon in carbonate. Well, one thing that we need to remember is the oxidation state of oxygen in compounds is -2. And this is true the vast majority of the time. So we want to remember that oxygen usually has an oxidation state of -2. Remember that if you have something like elemental oxygen, O2, the oxidation state is 0, because the oxidation state of any element is 0, and that'll come up in the next question. But here, in a compound, carbonate specifically, the oxidation state of oxygen is -2. We also want to remember that the oxidation states add up to the overall charge. So we want to do a math equation similar to what you would do if you wanted to find the charge on a metal in an ionic compound. So what we're going to do is we're going to take the oxidation state on carbon plus 3 times -2. There are 3 oxygens, each with a -2 charge, equals the overall charge, -2. So this -2 is the oxidation state of oxygen. There are again 3 of them. And this -2, the answer, is the overall charge. If this were neutral, this would be a 0. Then we get carbon, -6. 3 times -2 is -6, equals -2, plus 6, plus 6. Carbon equals +4. So we're using the oxidation state of oxygen, which is almost always -2, to find the oxidation state of carbon here. Don't forget that if oxygen is by itself, its oxidation state is 0. And if any element's by itself, its oxidation state is 0. Number 16 asks us, determine the reducing agent in the following reaction. So I wanted to remind you of Leo the lion says Gur. And what this mnemonic device is trying to tell us is losing electrons is oxidation. And where oxidation is occurring, we have the reducing agent. Because typically one thing is oxidized and one thing is reduced. So the thing that's oxidized is the reducing agent. It's reducing the other thing. And Gur means gaining electrons is reduction. And where reduction is occurring, we have the oxidizing agent. So what we need to also remember is a couple of other things. The oxidation states of elements are 0, and the oxidation states of metals in these simple ionic compounds is equal to their charge. So in this case, what we have is the oxidation state of this lithium being 0, and the oxidation state of this iron being 0. Why? Because they're by themselves. They're elements, right? It's just solid lithium and solid iron. Now we need to know the oxidation state of iron and iron acetate, technically iron 2 acetate, and that is the charge at the oxidation state. To figure that out, we could take iron plus 2 times -1 equals 0. Well, how did I get that? It's the charge on iron plus 2, because there's 2 of them, times the charge on acetate, which is -1, equals 0, the overall charge on this species. And when I do that math, I find out that iron is plus 2. So iron here is plus 2. What about lithium? Lithium is always plus 1. It's a 1A metal. Iron, we had to do that because it's a transition metal, so we had to figure it out. But lithium is always plus 1. It's 1A. So lithium went from 0 to plus 1. Its charge increased, so it lost an electron. This is oxidation, or said another way, lithium is the reducing agent because it reduced iron to plus. In the case of iron, we have something that's plus 2 going to 0. Positive 2 has to gain electrons to get to 0. So this is reduction, and the iron 2 plus is the oxidizing agent. So when we look at this question, it says which is the reducing agent? Well, the answer to that is lithium, because that's where oxidation occurs. Question 17 says, give the net ionic equation for the reaction, if any, that occurs when aqueous solutions of K2S and FeNO32 are mixed. All right, so we want to look at these two things. Well, this is going to be a double displacement reaction. K is not going to stay with sulfur because then that's no reaction, which is a possible answer. But K is going to go with nitrate, and iron is going to go with sulfide. And what we need to do is we need to see if there's something that's not aqueous. Because if we just have aqueous ions floating around in solution, this isn't a reaction, it's just a mixture of ions. That's not a chemical reaction. So we need to form something that's not soluble. Well, potassium and nitrate are always soluble. If you look at the solubility rules, you're not going to find anything about iron, but you will find something about sulfide. Sulfide is generally insoluble. So we are going to form something that's insoluble. So if I want to write the overall reaction, I could start with K2S, aqueous, plus FeNO3, 2, aqueous, yields. And I'm going to form something that's not soluble. I should have written this a little further over. I'm going to have to write it down a little bit. So I need to find the charge on iron. Well, iron plus 2 times -1 equals 0. How did I find this? The charge on iron plus 2 times -1 equals 0. Well, in iron nitrate, there's 2 nitrates, each with a -1 charge, and the overall charge is 0, so the charge on iron plus 2 negative charges equals 0, or Fe equals plus 2. Now, I know that Fe is 2 plus, S, it's a 6A nonmetal, so we can cross them, and we would get Fe2S2, but we can simplify to FeS, solid. Plus, we have K plus and NO3 minus. We cross them, and we get KNO3 aqueous. So this is the overall reaction, and I didn't have room, so I had to write this a little bit down. But it asks us for the net ionic equation. Well, the net ionic equation is to form the thing that's not aqueous. So our product is FeS, solid. How do we get to FeS? Well, what do we need? We need Fe, and we know that that's 2 plus, and we know that it's aqueous, because it's aqueous over here, so it's breaking up into its ions. And we need S2 minus, which is aqueous as well. And when we do that, we get Fe2 plus S2 minus yields FeS, which is choice letter D. Number 18 says, which of the following is considered a strong electrolyte? Well, strong electrolytes are ionic compounds that dissolve in water. So we need to find the ionic compound that dissolves in water. Well, here, CH3SH only contains nonmetals. This is covalent. If we look at PbBr2, halides are generally soluble, but one exception is lead. So this one is insoluble. So therefore it's not a strong electrolyte. HC2H3O2 is also covalent. This one happens to be a weak acid and a weak electrolyte, but it's definitely not a strong electrolyte. KNO3 is the answer. We'll come back to that. C12H22O11. Again, no metals, all nonmetals, so it's covalent. It doesn't break up into ions. So here, the strong electrolyte is KNO3. Why? If I take KNO3 solid and I dissolve it, I get K plus aqueous plus NO3 minus aqueous, and these ions could carry an electrical charge, which makes it a strong electrolyte. So to have a strong electrolyte, you need ions in solution. Question 19 says, how many grams of NaCl are required to make 500 milliliters of a 1.500 molar solution? So recall that molarity is moles of solute per liters of solution. So the first thing I want to do is I want to convert this to liters by dividing by 1,000, which is 0.5000 liters. So by way of a plan of attack, what I want to do is I want to convert from liters of NaCl to moles of NaCl, and then finally to grams of NaCl. So this is my plan of attack to tackle this problem. And what you'll notice is I can convert from liters to moles. In the past, the only thing that we've been able to convert to moles is grams. But now we have a new unit that we can convert to moles, which is liters. So I want to here, or in this question, convert liters to moles. Well, how do I do that? Well, first I want to start with 0.5000 liters of NaCl. And then I need to realize that 1.500 is moles per liter. How many liters? It's moles per 1 liter. So I want to put 1 liter of NaCl on the bottom. And how many moles of NaCl are in 1 liter of this particular solution? 1.500 moles of NaCl. This means 1.500 moles in 1 liter. We can write it out like this, and it'll allow us to find moles of NaCl. Notice this now allows us to convert a liters of volume and a molarity into moles. Just like in the past, we've converted grams and a molar mass into moles. Speaking of that, we now need to convert moles back to grams. So we want moles to cancel out, so we put 1 mole of NaCl on the bottom, and on top the molar mass, Na 22.99 plus 35.45, which gives 58.44 grams of NaCl, which is equal to 43.83 grams of NaCl. Question 20 says, how many milliliters of a 0.266 molar NaNO3 solution are required to make 150 milliliters of a 0.075 molar NaNO3 solution? So here we have a concentrated solution and we want a more dilute solution. For this, a good way to do it is C1V1 equals C2V2. C stands for concentration, V for volume, 1 stands for initial, and 2 stands for final. So this is basically the initial concentration times the initial volume equals the final concentration times the final volume. Well, in this case, the initial concentration is 0.266 molar. The initial volume, that's what we're trying to figure out. What do we want to make it into? Well, we want to make it 0.075 molar. And how much do we want to make? We want to make 150 milliliters. For C1V1 equals C2V2, you can actually use the volume in milliliters. However, if you're not sure, you can convert it to liters. In the previous question and in the next 2 questions, you are going to have to convert those volumes to liters. Here to solve this, you take the 2 numbers, multiply them together, divide by the number next to the variable, and you find that V1 equals 42.3 milliliters, which is the volume of this. We need to make 150 milliliters of this. This is choice letter E. Question 21 says, how many milliliters of a 0.55 molar hydroiodic acid, this one, solution are needed to react with a 15 milliliters of a 0.217 molar cesium hydroxide, this one, solution? So essentially we're doing an acid-base reaction here, and all the stoichiometric coefficients are 1, and we get a salt and water. So what we want to do is we want to do what is I call solution stoichiometry, or I think it's commonly called solution stoichiometry. In this case, we need to use the information about the cesium hydroxide to find something out about the hydroiodic acid. So if we start with liters of CSOH, we can convert that to moles of CSOH. And I showed this in problem number 19. Converting liters to moles involves using a molarity, and we'll use it here again. Once I have moles of CSOH, I can convert it to moles of HI, and then, because it asks me how many milliliters, I can convert it to liters of HI, which I'll then have to multiply by 1,000 to find milliliters. So in this case, we can't use 15 milliliters. We have to convert that to liters, so we divide by 1,000 and we get 0.01500 liters of CSOH times. Now to convert liters to moles, we need a molarity, and we have one. This is 0.217 moles per liter. So in 1 liter of CSOH, there are 0.217 moles of CSOH. We've now found moles using the molarity. Now we're converting from moles of one compound to moles of another. And just like when we did use grams, moles of one compound to moles of another involves a balanced chemical equation. In this case, it's 1 mole of CSOH for 1 mole of HI. We then want to convert to liters of HI. Well, we know that there are 0.550 moles in 1 liter of this HI solution. But in this case, we want moles to cancel out, so we put the 0.550 moles of HI on the bottom and the 1 liter of HI on the top. And when you do that, you get 5.92 times 10 to the minus 3 liters of HI. But the question asks for it in milliliters, so we have to multiply that by 1,000, and we get 5.92 milliliters as our final answer. Finally, question number 22 says, what mass in grams of AgCl is formed from the reaction of 75 milliliters of a 0.078 molar silver acetate solution with 55 milliliters of a magnesium of a 0.109 molar magnesium chloride solution? So in this case, we have the number of moles, essentially. We have a molarity and a volume of both the silver acetate and of the magnesium chloride. So this is a limiting reagent and solution stoichiometry question. This is a bit of a doozy, but I think it's a good question because it's really good practice. So let's do both and then figure out which one gives us less of the silver chloride, because that's going to be the theoretical yield. So to do this, we first start with our silver acetate. Just because it came first, you could start with the magnesium chloride if you wanted. So we want to go from liters of Ag C2H3O2 to moles of Ag C2H3O2. Then we're trying to figure out how much silver chloride we can make, so we want to go to moles of AgCl using the balanced chemical equation, and then finally grams of AgCl using the molar mass. So that's basically our plan of attack. We want to do the same plan of attack for magnesium chloride. So in this case, we want to go from liters of MgCl2 to moles of MgCl2 to moles of AgCl, and then finally to grams of AgCl. So we're going to do this for both of our reactants, silver acetate and magnesium chloride, and we're going to find out which one gives us less silver chloride. So how do we do that? Well, if we start with 0.0750, we divide that by 1,000, liters of AgC2H3O2 silver acetate times. To convert from liters to moles, you need a molarity, in this case 0.078 molar. So this means there are 0.078 moles in 1 liter. We want liters to cancel out, so we put it on the bottom. 1 liter of AgC2H3O2, and on top, the molarity number of moles, 0.078 moles of AgC2H3O2. O2. Now we want to convert to moles of AgCl. We use the balanced chemical equation. So there's 2 moles of AgC2H3O2 for every 2 moles of AgCl. So we use a balanced chemical equation to go from moles to moles. Now we want to convert it to grams. We use the molar mass. So we use Ag plus Cl. We put 1 mole of AgCl on the bottom, and the molar mass, when you add those together, it's 143.32 grams of AgCl. And when you multiply by the top, divide by the bottom, and repeat all the way across, you get 0.38 grams of AgCl. So using all of our silver acetate, we can get 0.838 grams. Now let's figure out how much we can make using all of our MgCl2. It's the same idea. We want to convert those milliliters to liters. So we start off by 0.550 liters of MgCl2 times, well, we know that it's 0.109 moles per liter, so we put the 1 liter of MgCl2 on the bottom and the 0.109 moles of MgCl2 on the top. Now we want to convert from moles of MgCl2 to moles of AgCl. We're going to use the balanced chemical equation. So we put 1 mole of MgCl2 on the bottom, because there's a 1 here, and we put 2 moles of AgCl on the top, because there's a 2. Then we're going from moles of AgCl to grams, moles to grams, same conversion, so same conversion factor, 1 mole of AgCl on the bottom and 143.32 grams of AgCl on the top. Multiply by the top, divide by the bottom, repeat all the way across, and you get 1.72 grams of AgCl. So what you find is that the theoretical yield is the lower one, so this is the theoretical yield, because when I make 0.838 grams of AgCl, I have no more silver acetate. If I have no more silver acetate, I can't make any more silver chloride. So this is the amount that you're going to make, which is choice letter B. I will point out that there is a mistake with the sig figs here, because this is only 2. You could argue that this should be 0.84, but they got 0.838, so I'm just going to go with it. But that's basically the idea here. I hope you found this exam helpful, and basically I strongly recommend you use the description down below to click on the questions that you most want to see.